Hello, Chem 201 Organickers. We are going to be starting Chapter 3 also this first week of our accelerated summer session. What we're going to be doing is looking at what organic chemistry really is all about. We're going to start looking at carbon compounds, and we're going to focus in this week on sections 3.1 to 3.5 in our textbook. This is the time where you might want to bring your models around, because the models are going to be really, really important in looking at these things in three-dimensional space. When we get into conformational analysis a little later, when you want to see if something is the same structure or different structure, a lot of times if you make your models, these things can really help us determine if something is the same or different. And I love models in organic chemistry. If you don't use them, a lot of times you're going to really struggle with trying to see these things in 3 dimensions. So let's get started. And I will share my screen. All right, so we are looking at alkanes and cycloalkanes. So when you think about these, what you want to notice is that alkanes are considered to be hydrocarbons. So alkanes have hydrogen and carbon, and that's all. I only have those 2 elements when I'm talking about an alkane. Now, if I put carbon and hydrogen together, I can get something that's saturated, which means my valencies of carbon are all single bonded. So I don't have any double bonds, I don't have any triple bonds. What I have is a fully saturated, every carbon has 4 other atoms attached to it. And that would be not 4 bonds, but 4 other atoms attached to it. Or I could be unsaturated. And this is where I have my double bonds, my triple bonds, and my aromatic rings, like benzene. So this carbon is not saturated. I don't have as many hydrogens as I possibly could have around those carbons because I have this double bond. Same thing with these carbons. Those carbons are unsaturated because instead of having as many hydrogens as I could, like in this structure, what I have is fewer hydrogens because I have double bonding that's occurring. So you have to be able to recognize what's saturated and what's unsaturated in terms of our hydrocarbons. Alkanes are going to be unsaturated. This is where I'm going to look at just carbon-carbon and carbon-hydrogen single bonds. That's what I'm going to focus on when I study alkanes. So here's sort of a flow chart about hydrocarbons. If this is all of the compounds that contain just carbon and hydrogen, I can break this down to saturated and unsaturated. We're going to focus right now in Chapter 3 on alkanes and cycloalkanes. So remember, the key feature is I have only carbon-carbon single bonds. Every single valence on this carbon is actually filled with a single bond. Now, alkenes are considered to be unsaturated. Alkynes are considered to be unsaturated, and arenes are considered to be unsaturated. Notice we will get to those in later chapters in this book. But the basic idea is for an alkene, I have carbon-carbon double bonds. For an alkyne, I have carbon-carbon triple bonds. So here's my double bond. Here's my triple bond. And then for an arene, I have a benzene-like ring, which is this hexagonal structure with alternating single and double bonds. So alkanes are saturated hydrocarbons. They contain the maximum number of hydrogen atoms possible for the number of carbon atoms present. There is actually a generic formula for an alkane, which is CnH2n plus 2. The N is the number of carbons. So if I have one carbon, I have C1H2 times 1 plus 2. If you recognize that, that's methane. If I look at 2 carbons, I have C2H2 times 2, which is 4, plus 2, which is 6. That's going to be ethane. The fact that all of these carbons are saturated means that in an alkane, every carbon atom is sp3 hybridized, which means the geometry around those carbon atoms is tetrahedral, and my bond angles are approximately 109.5. On this slide, I show several different ways to represent alkenes. We're not going to group them into structures like I could call butane C4, H3, 4, 5, 6, 7, 8, 9, 10. I could call pentane C5, H12. I could call propane C3, H6, 9, 6, 7, 8, H8. But that doesn't really tell me anything. Remember, I want to look at structure in organic chemistry. So what I want to do is look at which atoms are bonded to another. So this is probably what you would be most familiar with. Propane has 3 carbons. Each carbon is bonded to the other carbon, and then each carbon is surrounded by hydrogens. So this is probably what is the easiest for you right now. This is what we're going to lean towards as we go into this class. Notice I have 1, 2, 3 points on that sort of bended line. And I have an angle. So this line is sort of staggered. Well, every point is equal to a carbon. And then the hydrogens are assumed to be there because they're going to fill up the valence on those carbons. So again, I have 1, 2, 3, 4 carbon atoms connected to each other. And then all of those hydrogens are assumed to be there. So I don't actually show the C for carbon atoms or the bonds and the H for hydrogen atoms as well. So how do I draw these? Carbon and hydrogen atoms are not shown unless I have to for special emphasis or clarity. Anything other than carbon and hydrogen are explicitly shown. So if I have an oxygen, if I have a halogen, if I have a sulfur or a nitrogen, those atoms are going to explicitly be shown. The carbon is assumed to be at the end of every line and at the intersection of 2 or more lines. So what I'm going to call this is I have carbon at the ends and the bends. So if I have something like this, here's a carbon because that's the end. Here's a carbon because that's a bend. Here's a carbon because that's a bend. Here's a carbon because that's an end. Multiple bonds are shown with multiple lines. So if I wanted to indicate a double bond somewhere, what I'm going to do is do this. Here I would have a carbon with a hydrogen, hydrogen, hydrogen. There'd be 2 hydrogens and then 3, because I have to complete all the valencies of carbon. Each one of these dots, right, is going to be carbon. But for the actual line formula, I'm just going to draw that. And then I'm going to assume to place all the hydrogens in order to give every carbon 4 bonds. So the proper number of hydrogen atoms that aren't shown are assumed so that they provide 4 bonds to each carbon atom. This also includes if I have formal charges. Now notice that hydrogen atoms on other atoms, such as oxygen or nitrogen, are explicitly indicated. So maybe I have this structure and I know I have a hydrogen. So this oxygen is explicitly shown. Here's a carbon, here's a carbon, here's a carbon. I have 3 hydrogens on this carbon. I have 2 hydrogens on that carbon. I have 2 hydrogens on that carbon. And again, those are implied and not shown. This hydrogen is explicitly indicated. Now, here it says lone pair electrons are not normally shown unless needed for special emphasis or clarity. I like you to show your lone pair. So again, if I had this oxygen, I could put my lone pair on those oxygen, and that sort of shows how the octet is filled around that atom. In the book, they're not going to show them unless we need them, but lone pair are going to be so important as we go forward that I really want you to get into the habit of actually doing that. So let's look at this. I have CH3, CH2, CHCl. Now remember, that means that both of those atoms, the hydrogen and the chlorine, are on the carbon. Then I have CH2. Remember how I read these, left to right. The hydrogens are there. The hydrogens are there. If I sort of stagger them, right, I have 1, 2, 3, 4, 5 carbons. So I would have 1, 2, 3. Notice I have this chlorine there. 4, 5. That might be a way that you're going to start. But then all I'm going to do is draw the line and not show the carbon. So this, or the hydrogen. So that's my line angle structure for that compound. I have to show the chlorine. And this is a case where the lone pair really doesn't matter, but sometimes I put those in just for clarity. If I'm going to draw that, I could also draw it this way. It doesn't matter if I start up or down. So this one started down. I could go 1, 2, 3, 4, 5, and on my 3rd carbon is the chlorine. That's equivalent to that. You have to look at connectivity. You do not look at positioning on a piece of paper. You have to look at what atoms are connected to which other atoms, and that's going to let you see if a structure is the same or if it's different. Here, notice I have a double bond, and this is also a bond here. So I have 1, 2, 3, 4, 5, 6, 7, right? So this is how I get this structure. The hydrogen here is assumed. There's 3 hydrogens on this carbon. There's 3 hydrogens on this carbon. No hydrogens because that's full with the double bond. 1, 2, 3, 4 bonds are on that carbon. I have 1 hydrogen on that carbon, 2 hydrogens here, 2 hydrogens here, no hydrogens there because I fulfill the octet with the double bond to oxygen and the 2 bonds to carbon, and here's the other one. Again, a lot of times on oxygen, I'm going to put my lone pair so that I can actually go ahead and use that later. I can get really, really complicated with different structures. Look at this guy here. I have got all these rings. I've got a long chain, but this is a line angle formula for that ring, right? This tells me that I have a hydrogen here, and this is a carbon. I have a carbon with 2 hydrogens. I have a carbon with 2 hydrogens. Here, 1, 2, 3, I have 1 hydrogen. Here, I have 2 hydrogens, and so on and so forth. So you want to be able to actually go ahead and be able to write the condensed formula, which has all the hydrogens and the carbons, and also these line angle formulas. And this takes practice. You have to be really good at Lewis structures because you have to know where I have carbon atoms, where I have hydrogen atoms pretty well so I can take them out and use this line angle formula. So there's 3 hydrogens on that carbon. There's 0 hydrogens on this carbon because I have carbon-carbon double bond. That's my 4 bonds. No hydrogens here. I have my lone pair on my oxygen. Here, I have 2 hydrogens because I have carbon-carbon, right? I have to have 2 more bonds, which would be 2 hydrogens. This guy, I have 1, 2, 3 carbons. So I have 1 hydrogen attached to this carbon at this dot here. Here I have 3 hydrogens. Here I have 2 hydrogens, right? If I draw those in, it's going to look like here, like this. This carbon has double bond. I need 2 more bonds, so I have 2 hydrogens. 2 hydrogens here, 1 hydrogen there, and so on and so forth. So you really need to get practice going from line angle to condensed structure. Sometimes I can really draw it out and I take all of the, I have all of the different atoms in there. So if I want to write propane, sometimes I'm going to write a total structure which shows all my bonds, and that's not really considered a condensed structure. The condensed would be CH3, CH2, CH3. But especially in the beginning, I'll sort of alternate between all 3 of these. The line angle, the totally everything is drawn out, and then the condensed structure, so that you guys become really familiar with how you go from one to the other. Now, when I think about alkanes, again, I have this general formula. N is the number of carbons. The hydrogens would be 2 times N plus 2. So these are the names, the molecular formulas, and the condensed structural formula for the first 20 alkanes with unbranched chains. So I go from, notice this system, meth is 1 carbon, eth is 2 carbons, prop is 3 carbons, bute is 4 carbons, pent is 5 carbons, hex is 6 carbons. You need to know these prefixes. These prefixes are really important